This is our first video looking at the domain of the composition of two functions. In this video I want to find the domain of g of f, where f and g are given by these polynomials. So let's recall the picture for g of f. We are going to take some x value, apply f to it to obtain a result, and then apply g to that result. So when we think about the domain of g of f, the x values must be in the domain of f, right? In order to apply f to them, they must be in the domain of f. And then the result must be in the domain of g. So let's analyze the domain of g of f for these two functions. I'm going to start by putting down a schematic where I have the domain of f on one number line and the domain of g on another number line. And the exercise is really asking us to find the x values here whose image lands in the domain of g here, right? As long as that happens, then x will be in the domain of g of f. So, what's the domain of g? The domain of g is all real numbers, right? Because it's a polynomial. So, any image from f that happens to be a real number is going to be in the domain of the composition, because I can apply g to any real number whatsoever. What's the domain of f? The domain of f, well, f is a polynomial, so the domain of f is all real numbers, right? Any x value whatsoever, I can apply f to it, and its result is going to be a real number, so it's going to be in the domain of g, and therefore I can apply g to the result. So the domain for g of f is going to be all real numbers. Let's look at another example and hope that a contrast makes this a little clearer. Suppose f of x is x minus 2, and g of x is the square root of x. Okay, so I need to think about the domain of f. I need to think about the domain of g. And I'm going to have to make sure that any images under f land in the domain of g. So what's the domain of g? Well, g is the square root of x. So I need to make sure that the expression underneath the square root, in this case just x, is non-negative. So the domain of g is 0 and all the x that are greater than 0. So now the question is, which x's here are going to land in the domain of g? Well, for starters, what's the domain of f? F is a polynomial, so the domain is all real numbers. When I apply f to any of these guys, I get x minus 2. So x minus 2 has to land somewhere in this graph. In other words, x minus 2 must be greater than or equal to 0. Solving that expression, we get x greater than or equal to 2. So the domain for g of f is 2 and all the x's greater than 2. Right? So let's recap here. If x is in the interval from 2 to infinity, then certainly it's in the domain of f, because f is larger than this domain. And moreover, when I apply f to any value in here, x minus 2 is going to be in the domain of G. Therefore, the domain of G of f is 2 to infinity. Close bracket around the 2 because 2 is included. Let's consider another example. Okay, so here I have an f and a g. I need to think about the domain of f, and I need to think about the domain of g. What's the domain of g? G is a polynomial, so its domain is all real numbers. So any image from f whatsoever, any real number that gets spit out of f is going to be in the domain of g, and so I'll be able to apply g to the result. What is the domain of f? Well, f is the square root of x minus 4, so I need to make sure the expression underneath the square root is non-negative, so x has to be at least 4. Any value on this any x value on this graph is certainly going to have an image under f that's in the real numbers, and I'll be able to apply g to that image. So the domain for g of f is 4 to infinity.